Now we can go to the next speaker, Metehan Yurt, who will present his paper, Fricative Phoneme Detection using Deep Neural Networks and its comparison to traditional methods. So Metehan Yurt is a research engineer in Germany, and he works on TGS synthesis.
Should I start? Hi everyone, my name is Mete. I am from Fraunhofer IAS, Erlangen, Germany, and today I will be presenting fricative phoneme detection using deep neural networks and its comparison to traditional methods. So there are 8 different fricative phonemes in English language, and in general fricative phonemes, they do not have clear form and structure, because they are produced by forming a constriction in the vocal tract that causes a frication, a turbulence, which in turn generates a noise-like sound that makes them difficult to analyze. So there are 2 main motivations behind fricative phoneme detection. The first motivation is in hearing aid industry. High-frequency hearing impaired people, they have difficulties to understand fricative phonemes since they contain high-frequency information. So if you are able to detect fricative phonemes in real time, you can do certain processings on them, so you can help hearing impaired to distinguish and understand fricative phonemes. So one example of this process is actually frequency transposition. You can transfer the high frequency content in the lower bands so that the hearing impaired can start distinguishing fricative phonemes. And the second motivation could be enhancing the audio quality, speech quality in audio codecs. Since we window the time domain audio, in time domain we have spectral smearing at the end. And if spectral smearing coincides with fricative phoneme borders, this also drops the speech quality. So again, if we detect fricative regions, we can adapt our windowing time resolution, and then we can avoid coinciding with fricative regions. Classical methods, traditional methods, they are extracting features related to fricative phonemes. These could be frication ratios, linear prediction coefficients, zero crossing rates, first and second peak frequencies, and band energy ratios. However, extracting features might be misleading because fricative phonemes, especially, they have different characteristics in themselves. So if you look at top 4 fricative phonemes, this S, Z, SH, and ZH, we see that most of their energies are concentrated in high frequencies. However, if you look at F and TH, we see more flat spectrum. And finally, if you look at V and DH, it is more or less the opposite. The concentration of their energies are actually lying in low frequency regions. So deep learning, of course, applied on fricative phoneme recognition, phoneme detection. Typically, male-frequency substitute coefficients are extracted from overlapping 20 milliseconds long time windows. And also contextual information is also used, meaning to be able to detect frame K in figure 3, people are introducing more delay and then use feature samples as well. This actually was proven successfully, so it was helping to detect or recognizing phonemes. However, for real-time application, this might not be a good idea because this incurs a lot of delay, and you cannot do this on hearing aids or audio codecs. This was the first outcome from the deep learning, and the second is actually 1D convolutional neural nets. They were proven to be useful for extracting problem-specific low-level features, and they were letting better phoneme recognition posterior probability estimations compared to the MFCCs. So with this motivation, we wanted to analyze deep learning to detect fricative phonemes, and we want to compare it against our traditional methods in Fraunhofer IAS. So this is our deep learning model. So it takes time domain monochannel signals in 20 milliseconds audio frames at 16 kHz sampling frequency. It is fully convolutional, and it outputs posterior probabilities for the event that the sample at the center of the input frame belongs to 3 classes of sounds. These are fricative phonemes, non-fricative phonemes and silence regions. We use timid dataset to train our model and do the benchmarking. Sorry. Timid dataset is a nice dataset because it is very common in phoneme detection, phoneme recognition research, and it's easy to benchmark. And here in this figure 4, you see one example sentence from the timid dataset. You have the time domain audio, and also you have the phoneme annotations which are aligned in time. So we didn't do anything fancy. We use the entire training set of the timid dataset for training set. We use the test set, which is the core test set of timid dataset, and we use the validation set, which consists of 50 speakers, and it's very common in the phoneme literature, and it's disjoint from training and test sets. We did one thing different, so we excluded essay sentences from the data set because these essay sentences are common for all speakers. There are 630 speakers and they are all speaking same 2 essay sentences. So we excluded them because if we didn't, the model might conceivably memorize the phonemes in these sentences using the training set and could make near perfect detection for these sentences in the test set. So this would make the model perform better than it does in reality. So we didn't do anything fancy in terms of the post-processing. So for the training samples, we did only standard deviation normalization, and we labeled 3 classes of phonemes, as I said before. So fricative phonemes, these are 8 fricatives. Unvoiced non-fricative phonemes, these are silence regions in the speech, and also we labeled finally voiced non-fricative phonemes, which are the rest of the phonemes in English. So we evaluate the deep learning model on the core test sort of timid data set. There are 192 sentences, and it lasts almost 600 seconds. So in figure 5, you see on top, the blue signal is the time domain signal. We take each of the sentences from the core test set. We take the black rectangle window you see. We shift this window from left to right at one sample at a time, and then we feed to our network. So this is 20 milliseconds long window, and then in below figure you see the in blue the posterior probabilities from the model, and also the orange line, which is the ground truth fricative regions. So before I show the evaluation results, maybe it is nice time to talk about the evaluation metrics. We use recall, precision, and F1 score. So recall is the detection rate through positive divided by the positive samples. Precision, on the other hand, measures the kind of robustness of your detection. So it measures how many of the fricative samples, detected fricative samples, were actual fricatives. So it kind of measures the false alarm, false predictions in your model. And F1 score is the harmonic mean between recall and precision. So in this table, we showcase the detection rates in percentage, and we achieved almost 93% unweighted average recall. We used unweighted average recall because the core test set was highly unbalanced. We also break down the performance into individual fricative phonemes, and we noticed that voiced non-sibilant fricatives clearly hard to detect, meaning V and DH. I will come to that later, why this is the case. And ZH and TH were also not so good for the model, but this could be explained by the representativeness of these phonemes inside fricatives, because they were leastly represented compared to the other fricatives. So if we pay close attention to V and DH, and if you look at the time frequency representation, as I stated before, they have a different structure in time frequency representation. The majority of their energy are lying in low frequency bands, and this is actually this makes the model confuse maybe with the vowels. On the other hand, after we evaluate the performance of the deep learning model, we retrain our classical method baseline algorithm, which is extracting features related to fricative phonemes. We are extracting zero crossing rates, gradient indexes, and high frequency to low frequency band energy ratio. If you look at figure 8, you see that these 3 features are actually really differentiating fricative regions. And here in this table we compare the deep learning with the classical baseline algorithm. It's clearly seen that the deep learning actually outperforms the baseline algorithm, especially if you look at the precision for fricative in the baseline algorithm. So it's almost 50%. So it's making too many false positives detections compared to the deep learning model, which is quite important for hearing aids and also audio codecs. You don't want to detect not fricative regions as fricative because it's actually expensive. And after we were clear that the deep learning model actually outperforms the baseline, we also evaluate the deep learning model on perceptually coded speech signals in telecommunication applications. We are using codecs to perceptually encode and decode the speech at lower rates, this really, depending on the bandwidth availability, this lowers the speech intelligibility. So if we can detect phonemes, especially fricatives, we can enhance the speech intelligibility. So we coded the timid core test set, and without retraining, we evaluate the performance of the deep learning model. And even without the retraining on perceptually coded data, the model actually performs more or less the same. So small performance degradation was there. With this findings, after this finding, we also thought that why not to bandwidth limit the coded timid files, because the limited bandwidth also limits the speech quality. So we also encode the core test set of timid dataset, and then we apply low-pass filtering on it. And then without retraining, we again evaluate our model. Of course, high performance degradation was observed because we were applying 4 kHz low-pass filtering. And then we retrained the model with the entire timid dataset encoded and low-pass filtered again, degraded, but comparable results were achieved compared to the original timid files. So this shows that with an inclusive and well-balanced training set, the network is capable detecting fricatives even on coded bandwidth-limited signals. So this table shows the evaluation of the model with and without retraining on perceptually coded low-pass filtered timid dataset, and we achieved almost 91% unweighted average recall for fricative detection, even with the bandwidth-limited speech signals. Finally, we compared the deep learning model against the state-of-the-art that we see in the literature. So it was a classical detection procedure. They were extracting zero crossing rates, first and second peak frequencies, and band and edge ratios. And however, we see that their evaluation process is slightly different than ours, because they were excluding voiced fricative phonemes, which includes V and DH, and we know that V and DH are really hard to detect among fricatives. So they were also not excluding SA sentences from their test sets, and they were applying non-causal post-processing on it. So we applied the same procedures to reach a fair comparison, and then we reach mostly almost 96% unweighted average recall. So of course there is a computational consideration with deep learning models. Our baseline approach, our home approach, is actually more applicable for real-time applications such as hearing aids or audio codecs. But deep learning model has better performance, and it will be applicable for real-time applications after further optimization. So all in all, deep learning model is better compared to the baseline algorithm, and also achieves state-of-the-art accuracy results. So with that in mind, the deep learning model will be further optimized for complexity in the future research. Finally, I want to mention that our source code and the model that we use in the paper is in our GitHub repository. One can take it and use it for his or her research. One can optimize the model that we suggest, and finally one can train even different model for detecting other phoneme classes, or even for single phonemes. You can take it and then train a network that can detect phoneme T, for example. Thank you for your attention, and please ask your questions.
Thank you for this presentation. So now we have time, 7 minutes for questions.
Yeah, thanks for the presentation. I'm from ASR and phoneme recognition, actually. And when we do recognition on the timid database, there's some kind of a phone-based language model involved that gives you probabilities on transitions between phonemes. Did you include something like this, some linguistic knowledge, or is it a pure acoustic decision that you
It was pure acoustic model. We didn't use language modeling.
Because of computational constraints, or?
Because of both computational constraints and we just wanted to compare classical model versus deep learning, so we didn't want to include language modeling. But of course it helps a lot, but it comes not free, so.
Yeah, of course. And a follow-up question maybe, do you also use some kind of temporal context for the decision?
No,
model, like recurrencies, or just?
No, model just takes 20 milliseconds time domain audio, and it's in time domain, so single feature, so to say. So the convolutional layers on top, just extract features. But it's also a nice idea.
Thanks.
There are many written questions. First one is from Sébastien Lemaguet. Do you know if the false positives of the classical methodologies are widespread, or are they falling into some specific phonetic categories?
Yeah, especially classical model was throwing too many positives for V and DH. So it was always classifying V and DH as not fricatives. But this was for false positives, right? So the question was focused on false positives.
Yeah,
so, yeah.
It seems so. Another question from Yuri Mitai. Any numbers of runtime of the CNN versus ZCR, BRR, and so on?
Sorry, can you repeat?
Any numbers of runtime of the CNN versus ZCR, BR, and so on?
Well, I didn't get the question directly, but you are talking about convolutional layers versus RNNs, or the question?
I don't know if that's not my question. So.
Sorry.
Okay, and the final question, and didn't you try to use ZCR, BR, and so on instead of MFCCs as input to your deep neural network?
We didn't try using MFCCs. We did not use MFCCs, but maybe in the future research along with MFCCs we can try RNNs, GRUs especially, because they show maybe limited performance compared to convolutional layers, but it's really optimized compared to convolutional layers, I would say.
I'll just follow up on that. Did you? I mean, your baseline had a number of traditional signal processing features, and using these as input to a deep learning deep network could also be investigated.
We also actually tried that, but the performance was not improving. So we actually tried band and edge ratio, especially to distinguish V and DH compared to the vowels, actually, but it did not help. Especially, we also not the energy ratios, also the energy per se, but we couldn't get better performance.
What is the classifier used for traditional baseline approach?
It was naive Bayesian classifier.
And if it's a simple classifier, does it mean that the low performance is because of the simple classifier?
Yeah, maybe, but we did not actually work on that. But it's normally in classical methods people are using linear detectors, so we also did the same. But maybe using those features we could try maybe multi-layered perceptrons, fully connected layers. This could also be in the future research. Worth to try, actually.
Does it make sense to try a MLP to classify encrafted feature for fair comparison?
I think it makes so. It makes a good comparison, actually.
Okay. Any other question? Maybe I have one final question. It's do you know if the errors for different fricatives are speaker specific, or do you know what kind of phonetic context or speakers make the errors? Or
we actually didn't consider this. So there are different speakers, but we did not focus on speaker specific error rates. but yeah, it could be worth to look as well.
Okay.
One final thing. We have 1 more minute. You chose to have 2 classes for the non-fricatives. Why is that?
Sorry again.
You had your classifier was a 3-way
yeah,
classifier.
yeah.
Why did you use 2 classes for non-fricatives?
Some silence regions, they were detected as fricatives because there are no energy, and the model was saying that, okay, this could be a fricative phoneme, so we decided, okay, we should split non-fricatives, speech and non-speech, so that was the reason. So because it was confusing the model because there are low energy with silence regions.
But you also showed some differences between the fricatives. Could it be a way of improving performance to introduce, say, 2 classes for the fricatives as well?
Yeah, could actually would be really interesting to try that. Maybe even 3 classes among the fricatives. Yeah, would be nice to try it as well for the future research. Thank you.
Yeah, I think it's time to finish. So thank the speaker again.